Hello everyone, I'm Lee Pang, a genomics specialist with Amazon Web Services.
Hey everybody, I'm Ruchi Munshi, a product manager over at the Broad Institute.
And in this video, we're going to give you a couple demonstrations of running Cromwell on AWS. If you haven't already, I recommend that you watch our webinar that goes into the details of genomics workflows, patterns and services, and how to use Cromwell. As we covered in our webinar, here are key considerations when working with genomic data. First, genomic data sets are big. Depending on the amount of detail, a single genomics experiment can range from tens of gigabytes to several petabytes. Second, converting raw DNA sequencer data to scientific insight takes a lot of computational steps, each with their own unique resource requirements. Handling genomic data involves processing pipelines or workflows. So for example, here is the Broad's Genome Analysis Best Practices workflow. As you can see, there are many steps to get to the data that scientists would use for analysis. This is where Cromwell comes into play. Cromwell is an open source workflow orchestration engine that runs both on local machines and in the cloud. Cromwell reads workflow definitions written in languages like WDL or WDL and CWL, and then launches the resources needed to run the jobs defined. With AWS, Cromwell acts as an interface to AWS Batch. Workflow jobs are submitted to batch queues and run on batch compute environments. In the next few minutes, I'm going to walk you through setting up Cromwell on AWS and running a simple workflow. To start, you're going to need the following things: an EC2 instance to serve as your Cromwell server, a custom AMI for running genomic workflow jobs and talking with Cromwell, an S3 bucket for workflow inputs and outputs, and a batch compute environment and job queue. The first thing you're going to need to do is create a custom AMI. So if you head over to our documentation site for genomics workflows on AWS and go to the section on creating a custom AMI, you'll find a couple of CloudFormation templates that you can use to walk you through the process. Hit Next. Pick your AMI type. In this case, you want to pick Cromwell, and specify the scratch mount point as Cromwell root. And hit Next again. And Next one last time. And click the checkbox to acknowledge that AWS CloudFormation will create IAM resources, and hit Create. When the process completes, select the stack and take note of the AMI ID on the Outputs tag. You'll use this ID later when you set up your batch environment. To create the remaining resources you need, you can use the CloudFormation stacks that we've provided in our genomics workflows documentation. You can either use the full stack, which creates your S3 bucket, VPC, IAM roles, and batch job queue and compute environments, or you can use a CloudFormation template that will launch these resources in an existing VPC, or you can use individual templates for creating the S3 bucket by itself, IAM roles, and the AWS batch environment independently. To use these, simply click on the button, click Next, specify your AWS bucket, key pair, availability zones, and provide the AMI ID. Use the AMI ID that you created using the custom AMI script. Hit Next, and Next again to create your infrastructure. When your infrastructure is complete, go to the batch stack, go to Outputs, and record or take note of the 2 job queues that were created. In this walkthrough, we're going to use the high priority job queue. Copy this value for later. Next, you're going to need to create an EC2 instance that will act as your Cromwell server. Go to your IAM management console and create an instance profile that this instance will use to access AWS services. Attach inline policies to this role to allow it to create jobs and job definitions in batch. And allow read-only access to your bucket in S3. Next, go to your EC2 console and launch an instance specifying the instance role you just created. When your instance is available, connect to it via SSH. Once you connect to your server, download the most recent version of Cromwell, and create a config file. Replace the placeholders for S3 bucket and batch QARN. Create the following files: a hello WDL file with a single task called hello and a workflow wf_hello that calls that task. This task will simply echo the command hello and addressee welcome to Cromwell on AWS. It'll use another file for inputs in this input file, put this JSON formatted data, wf hello.hello.addressee and world. You may now start the Cromwell server on your EC2 instance. In this case, I'm using an SSH tunnel between my local machine and the remote instance on port 8000. So I can navigate in a web browser to localhost port 8000 and see Cromwell's Swagger UI. We can use this to submit the workflow that we created in the previous step. While this workflow runs, you can monitor its status in the logs or via the AWS batch console. Here we see one job has been submitted and is in the runnable state. You should see that the desired CPU count increases when the job is ready to start, and that in the EC2 instance or in EC2 management console, you should see instances queuing up. When the workflow successfully completes, you should receive a notification. And you should be able to see successful completion in the logs. You should also be able to find outputs that the workflow generated in your S3 bucket. So that concludes my part of the demo. I'm going to hand it over to Ruchi, who's going to show you something a little bit more complicated.
So the next workflow we're going to demonstrate in terms of running Cromwell on the AWS batch backend is what we call a Haptype Color workflow. And the Haptype Color is the GATK's leading germline color tool with a focus on short variant discovery. So in the case of this workflow, the input is a BAM file that goes through two specific tasks where Haptype Color, which performs short variant discovery on a single sample across multiple genomic intervals. So we see a scatter step taking place, which splits up the genomic data into various shards and then performs Haptype Color or runs Haptype Color or variant discovery across those shards. And then there is a final step to merge those various shards into a final GBCF file. So that's the sort of flow for this workflow. And this is a publicly available workflow provided by the GATK. In addition, in this case, I've collected all the required input files needed for this workflow, such as a sample input BAM, all the reference files, the dockers where the command is encapsulated, and sort of the other optimization parameters. In addition, in order to be able to run Cromwell on AWS, I also require an AWS config. So this is very similar to the config Lee presented earlier, except I have my own execution directory as well as my own batch queue that's been configured for use. So now I'll jump over to my terminal window to show you what it's like running Cromwell from the command line mode to run the Haptype Color workflow. For the purposes of this demo, I've collected all the files that will be required to be able to run a workflow on Cromwell on AWS. So for example, I have the inputs JSON we just looked at, which are all the inputs files required for the workflow, the actual WDL file, which is the workflow descriptor file, the AWS config, which includes information about the queue where these jobs are going to be dispatched. I have a Cromwell jar that I've downloaded. So that's all that's needed to get started. So what I'm going to do is string together the various components into the required command for Cromwell. So the first thing I'm going to do is point to the appropriate config file and then the appropriate Java file. And then the next required component for running Cromwell on the run mode, or what we call command line mode, is the path to the WDL. In this case, it's available right within the same directory, along with an inputs file, which uses a -i parameter and the file path to the inputs JSON in this case. And that's all that should be needed to start out the run. You'll notice from observing the screen in a couple of seconds that the Cromwell logs can be quite verbose. But we'll see sort of a color shift when jobs have been initialized, prepared, and dispatched to the AWS batch backend. I'm starting to see this is the actual task definition that was written inside of the workflow. So I'm seeing instantiations of it being sent to the batch backend. And jobs that have started running. So while this workflow runs in the background, and since this is a fairly computationally intensive workflow, even when running on a downsampled data set, it's going to take quite some time to finish. So what I've done in place for this demo is to copy down the results from the S3 bucket. So I have a results directory here, which includes all the outputs files generated by one of the tasks in the workflow. So if you're wondering how you would find these outputs themselves in the AWS bucket as well, then inside of your Cromwell config itself, you've declared the S3 bucket used to store your outputs. So if you look at your AWS config, there's a key called root, which includes an S3 file path. So in this case, all the various workflow executions performed using this config file all fall within that structure and within that bucket in S3. So what I'm going to do is list this directory that I've specified in my AWS config file to make sure that the workflow outputs are being added there as I would expect. So using the AWS CLI, I can ls this directory structure. Haptype Color is the name of my workflow. I can take an example run from the past. I can look specifically at the outputs of the Haptype Color job or the merge GVCFs job. And since this job was sharded across a single sample over various genomic intervals. I'm just going to take the first one. And here are the various output files generated by this particular task. There's something called, which is the rc.txt, which is the return code file, which represents the return code essentially returned by the program that was executed inside of the command, the standard error and standard out produced by the command as well, along with any outputs declared in the task definition. So since we have local copies of the results, we can start off by checking out the contents of the RC file. So if a job succeeds, at least when using GATK, the expected return code is 0. And this is something that can differ from various tools. But in this case, assuming that my job succeeded, I expect the contents of the return code file to be 0. And in case of debugging any kinds of failures, the return code file is a perfect place to start to understand what was the final outcome of a command. Secondarily, it can also help when debugging to look at any contents inside of the standard error file. So in this case, the GATK outputted the actual command, the full command being run by the GATK, along with any default parameters that are being applied, which can be helpful, along with the standard out file, which includes just a lot of information being emitted by the tool. And it can be verbose, it cannot be, just really depends on the kind of toolkit you're using. And in this particular case, since my sample succeeded, I'm not going to dig too far into my standard out file, but instead, what I want to be able to do is just investigate the file contents of the actual output file generated. So I see that the VCF produced is right here. I'm going to, since this is a gzipped file, I can simply gunzip and extract the VCF inside of this file. And I should be able to head and look at the header of the VCF. So I know that my VCF was generated. The header looks as if expected with some of the sort of normal attributes for it. And so this gives me confidence that my job succeeded. And then you can take this VCF or the gzipped VCF and pass it down to a tool downstream. So while this job runs, the workflows presented here should simply reach success on the order of minutes.
Thanks, Ruchi. That was an awesome demonstration.
Thanks, Lee. I hope you all get a chance to try out the various tutorials, and we would love to hear any feedback you have.
So that concludes our demonstrations. If you'd like to learn more, I recommend checking out the docs for Cromwell and running genomics workflows on AWS, taking a look at Cromwell's GitHub repository, and looking at what you can do with WDL at openwdl.org. If you'd like to learn more about other scientific workloads on AWS, I recommend you check out our pages on research and technical computing. Take a look at our research cloud and cloud credits for research programs, and explore datasets we host on our registry of open data. And with that, I want to thank everyone for watching. I'm Lee.
I'm Ruchi.
Go build.